various topics. I have been working together with my collaborator Farhang Loran from Isfahan University of Technology in Iran. The title is Exactness of Born Approximation, Broadband Unidirectional Invisibility, and Implicit Regularization of Point Scatters in 2 dimensions. So I will give a general introduction to what I call dynamical formulation of time-independent scattering theory in 1 dimension, and then I talk about its generalization to 2 dimensions. And essentially, the main content of the talk will be various applications of this formulation, including broadband omnidirectional invisibility, what I call alpha equivalent potentials, exactness of the firstborn approximation, broadband unidirectional invisibility, and finally implicit regularization of point scatters. And I will give some concluding remarks. Okay, so by scattering in 1 dimension, I mean time-independent scattering theory defined by the time-independent Schrödinger equation, where the potential is a scattering potential. That means it dies quickly enough at infinity so that the general solution of the Schrödinger equation has plane wave asymptotics. And I will also allow this potential to be complex valued and even energy dependent. K is the wave number, K squared is the energy. So asymptotic solutions are plane waves, and these plane waves have these amplitudes. A's and B's are amplitudes of right-going and left-going plane waves at -infinity and +infinity. The sign is that. And you can define something called a transfer matrix as a 2x2 matrix which connects the amplitudes at -infinity to those at +infinity. These amplitudes are generally k-dependent, so M is going to be a k-dependent 2x2 complex matrix. Among the solutions of the Schrödinger equation are the scattering solutions. These are there are 2 of them. The scattering solutions corresponding to left incident waves, which is here. This is the incident wave which comes from the left where the source is at -infinity. Parts of it gets reflected and parts of it gets transmitted. And these are called the reflection and transmission amplitudes. And you can also have your source at +infinity and send a wave from +infinity. This would be the incident wave. This would be reflected and transmitted waves. And L and R means left incident and right incident. And just using these expressions for these scattering solutions and the definition of the transfer matrix, you can connect the reflection and transmission amplitudes from left and right to various ratios of various entries of this transfer matrix. And you can also show that the left and right transmission amplitudes coincide. This is called transmission reciprocity. So this says that if you know what the transfer matrix is, you have the complete solution of the scattering problem in 1 dimension. Well, in 2013, I was looking at this transfer matrix, and one of its basic properties which makes it useful and for various applications is that its composition property. Well, this says that if you can dissect your potential into 2 pieces such that the support of one of them, V1, is to the left of the support of V2, which means that V1 vanishes for x bigger than a for some a, and V2 vanishes for all x is less than a, and V1 and V2 add up to give you the original potential. All these 3 potentials are scattering potentials, so I can associate to them transfer matrices, which I call M, M1, and M2. Then it's very easy to show that the transfer matrix of the sum is the product of the transfer matrices of these component potentials. And the order of these 2 matrices has to do with the order of the support. The support of V1 is to the left of support of V2, so M2 comes first and then M1. And what I kind of thought of is that this is very similar, almost identical to the way you multiply evolution operators in quantum mechanics. So if you have a quantum system whose state vectors belong to some Hilbert space, the time evolution operator takes an initial state vector to a final state vector at t. It's a linear operator. If you want to evolve your state vector from t0 to t2, but going through this time t1, you can also evolve it from t0 to t1 and then from t1 to t2. These are achieved by this evolution operators u1 and u2, which I introduced here, or directly from t0 to t2, which is u. And just by simple multiplication of operators, you see that u has to be u2 times u1, which is very similar to this composition property of the transfer matrix. So I asked myself, is there a connection? Can I associate a quantum system so that this transfer matrix gets connected to the evolution operator of that quantum system? And the answer turned out to be the same. First, everybody knows you can, for general Hamiltonians, which are generally time dependent, the evolution operator, you can't find a closed form expression. What you can do, you can use the Schrödinger equation satisfied by the evolution operator, write it as an integral equation, and then use this equation for getting t0 here and repeat. This way you get this Dyson series, which turns out to be a time-ordered exponential of this operator. So the connection between evolution operator and transfer matrix is given by this theorem. It turns out that this transfer matrix of scattering theory is the evolution operator which evolves states from -infinity to +infinity, asymptotic evolutions, for a two-level system with this kind of a Hamiltonian, where the potential appears as a coefficient. And this piece is universal, has universal character. It's a non-Hermitian matrix, even if your potential is real. And if it's real, this happens to be pseudo-Hermitian. And the important thing here is that the evolution doesn't take place in time, but it takes place in space. It is X which plays the role of time. So in terms of the time evolution, time-ordered exponential, I can write M as time-ordered exponential from minus to plus infinity of H. This is essentially the definition of the S matrix in interaction picture. So let's try to look at scattering in 2 dimensions. Again, I use time-independent Schrödinger equation to introduce the scattering problem. I sent plane waves from some source with some wave vector, incident wave vector, which can make an angle θ0 with the x-axis. I call this incident angle. And then the wave scatters and goes off, again become plane wave with new wave vector k. Now you can use the famous Lippmann-Schwinger formalism from the Schrödinger equation written here in terms of operators and the free Schrödinger equation. You can derive the Lippmann-Schwinger equation, which is this. G plus is the outgoing Green's function. And its kernel or propagator in 2 dimensions is given by the Hankel function, H10. From this equation, you can take this term to the left and write it like 1 minus this psi equals to k0, and then formally invert this operator, get this, and expand this in a geometric series. This gives you a series solution for the scattering wave, which is called the Born series. you are interested in asymptotic form of the wave function. So you take r to infinity. R is the radial coordinate in polar coordinates. And from the Hankel function, asymptotics of Hankel function, you can show that the asymptotic form of the solution has this form. This is the contribution of the incident wave, and this is the scattered wave. This f theta is called the scattering amplitude, which is by definition related to the potential and the solution psi according to this formula. R theta are the polar coordinates. Now, we had this series solution. We can use it for here. So substitute this equation here, and then you get a series expansion for the scattering amplitude. Again, this is also called Born series for the scattering amplitude, where these terms of the series are related to various powers of V, G plus V. There are precisely L copies of V in FL. The nth Born approximation is the approximation in which you truncate the series solution after n terms. And the first Born approximation is when you keep the first term, which is F1, which has this form. And just looking at this formula, you see that this is precisely Fourier transform of your potential. This is the explicit expression for the what first Born approximation gives for the scattering amplitude. 2 tildes means I'm doing Fourier transform over x and y. I'm in 2 dimensions, and this is my definition of Fourier transform. So this is the Fourier transform. This is the first component. This is the second component. Now, one of the interesting observations you can make out of this equation is that, you see, if you know the first Born approximation formula for F1, you can do inverse Fourier transform and get the potential back. So this is a very simple way of doing inverse scattering. If you're sure the first Born approximation is good, you can get a fairly good estimate or idea about your potential. This was the standard approach to scattering in 2 dimensions. Now I talk about the way we approached it with Laurent in 2016. Our aim was to see if we can generalize this notion of the transfer matrix to 2 dimensions and use its nice properties like the composition property. So what we said was that let's take look at the x-axis in our setup for 2-dimensional scattering theory. We know that if we go to plus minus or minus plus infinity or minus infinity along the x direction, and since the potential is a scattering potential, it will die off fast enough, and we will get the solutions which in x plus minus infinity will look like a plane wave. So it will have, since I'm in 2 dimension, it will have an exponential of something times x and times exponential of something times y. So call this p, call this omega, and then you can get the most general expression which would satisfy the Schrodinger equation. It will look like this. But the coefficient of omega, which is essentially the component of p along x, is related to the coefficient of p along y because their square should add up to k squared here. So this omega of p is related to k and p like this. And as you see, since I want plane waves, this omega must be real. That means I'm not allowed to take p bigger than k or less than minus k. That I can make sure by saying that these coefficients, which can depend on p, will be 0 when absolute value of p is bigger than k. Okay? So this says that these coefficient functions, a plus minus, b plus minus, again, these correspond to plus minus infinity when x goes to plus minus infinity, they are functions which satisfy this condition. They vanish when absolute value of P bigger than or equal to K, and this gives you a function space to which this A plus minus and B plus minus belong. Now, once I have this setup, which looks very much to one-dimensional situation, I can define the transfer matrix to be the matrix which again connects the coefficients at minus infinity to those at plus infinity. The only difference is that these are not, A's and B's are not numbers, they are functions. And this matrix is not a numerical matrix, it's a 2x2 matrix whose components are linear operators. So M is actually a linear operator which takes the function space of two component waves, some wave functions, to two component wave functions, and these fk squared is just product of fk by fk. So components should satisfy this condition. So you might say, well, you can define anything you like, but is it useful? So the first property of this transfer matrix, which is completely counterintuitive, is that it can be expressed in terms of a time-ordered exponential, exactly like in the one-dimensional case. The Hamiltonian H is a 2x2 matrix Hamiltonian, but its entries again involve operators. In general, it's a 2x2 matrix with integral operator entries. This is the definition. Phi is a test function from this fk squared two component wave function. Sigma 3 is the Pauli diagonal Pauli matrix. K is this matrix. And this Vxi del P, formally it's what you get by replacing y by the I times derivative of P, but you can make it more rigorous. This is more explicit form of this Hamiltonian. So it's a 2x2 Hamiltonian. Each of these entries is an operator. This is going to be an operator, and it's a non-local operator. Actually, it's an integral operator. You can show that it acts on this function space fk according to this convolution integral. So V tilde is the Fourier transform of the potential with respect to y. So you take the Fourier transform with respect to y, you get V tilde, you substitute here, and then you perform this integration, and that defines this V. It's a linear operator, but it's non-local, it's an integral operator. Looks complicated, but is it useful? Again. So one of the things you can immediately see is that if it happens that this integral operator acts on this function space as zero operator, then this is zero, that makes H is zero. And if H is zero, then M is one, because the series expansion terminates after its first term, which is identity. And this I will use later. The second and more important property of this transfer matrix that I have introduced is that it determines the scattering amplitude. Here is the formula, it's an explicit formula, how you can get the scattering amplitude out of M. First, you compute this T minus and T plus, which involve entries of M and entries of one of them, inverse of the entries of M, the two entries. Which really, what this definition means is that, well, I have to apply M22 to both sides and solve this equation for T minus. M22 involves this operator, non-local operator V. So this is essentially this equation is an integral equation for T minus. You can solve that integral equation, you can get T plus using the second equation. So in order to solve a scattering problem using this method, first you need to calculate M, and then from M you get its entries. You solve an integral equation here, and then you get T minus and then T plus, and you substitute here, you get the explicit solution for the amplitude, scattering amplitude. I'll give examples, you'll see how it works. I mentioned that it may happen that this operator acts on this function space as the zero operator, in which case M is just identity operator. Well, if M is identity operator, then M1, 1 is 1, M2, 1 is 0, and M1, 2 is 0. So you see everything vanishes. So you get T minus and T plus identically 0. But if T plus minus are 0, then the scattering amplitude becomes 0. And that means that this potential does not scatter any wave. And that is a very direct route to invisibility. Our first result about achieving invisibility in this, using this method is this theorem. It says, suppose you pick some alpha positive real number and assume that the Fourier transform of your potential with respect to y vanishes for ky less than or equal to 2 alpha. Then the potential is omnidirectionally invisible for all wave numbers less than or equal to alpha. Omnidirectional means that it doesn't matter with which angle you send your wave, it does not scatter as far as the wave number is less than or equal to alpha. The wave number is proportional to frequency. So for low frequencies, you get nothing back. And there's no approximation involved. This is exact result. This is what I discussed in more detail in Bad Honef in 2017. You can get an optical realization of this effect if you have a two-dimensional setup where you have a non-magnetic isotropic medium which has translational symmetry along z-axis, which means that the permeability is 1, is the same as the vacuum, and permittivity depends only on x and y through this relative permittivity. And if you're interested in TE waves, whose polarization is along the z-axis, along the symmetry axis, then you can take this ansatz, substitute in your Maxwell's equation, you get the Helmholtz equation, and which you can write as the Schrodinger equation in 2 dimensions, with potential given in terms of the permittivity, like relative permittivity, like this is called an optical potential. So you can translate this theorem, write it in terms of permittivity. It takes this form. If eta is relative permittivity minus 1, and Fourier transform of eta with respect to y is 0 for ky less than or equal to 2 alpha, then this medium will be invisible for all TE waves with wave number less than or equal to alpha. Well, this is an example. You can easily obtain infinitely many examples which satisfy this condition. This is one particular example I worked out, and I arranged all the parameters of this alpha and L and everything which fits to reasonable values, experimentally detectable reasonable values. In this case, you see the X dependence is, I mean, the permittivity, the relative permittivity is 1 away from this interval 0a. So I essentially have a slab with thickness A, and only inside the slab there is modulation with respect to y. So it's a periodic type of modulation and with decaying amplitude. So if this can be approximated by a real finite slab, because as y becomes large, this decays very fast. So this setup, the prediction is that will be invisible for wavelengths which are bigger than or equal to 500 nanometers. That's green light. Okay. Next, I want to talk about this alpha equivalence. So what is alpha equivalence? Definition: potentials with identical scattering properties for wave numbers less than or equal to alpha we call alpha equivalent. So one example is this potentials that I introduced. They are invisible for k less than or equal to alpha, so they are equivalent to vacuum. They are equivalent to 0 potential. So this generalizes that situation. And what we could prove is that if you have two potentials which satisfy this condition, that means their Fourier transform with respect to y coincide for ky less than or equal to 2 alpha, they are equivalent. They will have the same scattering properties for wave numbers less than alpha, and different, presumably, for larger values of k. The proof of this is actually very, very simple. I have two scattering potentials. I can associate to them their transfer matrices, which come from their corresponding Hamiltonians. And what we did was to use this condition star to show that under this condition, these two operators, which corresponds to the potentials V1 and V2, coincide on this function space. Since these two operators are the same, then H1 is equal to H2, which means M1 is equal to M2, which means F1 is equal to F2. So you get the same scattering amplitudes, and this happens only for k less than or equal to alpha. Next topic is what I call quasi-exactness solvability in scattering problems. The statement of the result is as follows. Again, take some positive real number, and this time suppose that the Fourier transform of your potential with respect to y is 0 for ky less than or equal to alpha. Previously, we had ky less than or equal to 2 alpha. Now I assume ky less than or equal to alpha, which is weaker condition. Then we could prove that under this condition, the first Born approximation gives the exact expression for the scattering amplitude for wave numbers k less than or equal to alpha. And this is the first time ever that we could find a potential for which the firstborn approximation is exact. And the exactness is for low frequencies, so low energies. So there is an energy cutoff or frequency cutoff below which this potential is exactly solvable. That's what I call quasi-exact solvability for scattering problems. So the proof of this is also not very, very difficult. You're trying to get solvable problems. So one way of dealing with these problems is that it would be very nice if the Dyson series truncates. So we try to find conditions to make this truncate here. We had other examples that had that property. So we realized that with this condition, double star, this thing vanishes. That means if I pick two test functions from my function space and apply V twice, like this, I get 0. It's not very difficult. It takes like half a page of calculations to show it. But once this is done, then that means that if I pick two entries of my Hamiltonian and calculate their action, the product of their action on phi, I also get 0. And that says if the product of these two Hamiltonians will be 0 on this function space. Therefore, the Dyson series will automatically truncate after the second term. I mean, the quadratic term in H will be 0 and the other ones will give 0. Now, take this one to the left and apply it twice, you get 2 copies of H, which gives you 0. So by just simple algebra, you see that if I take any entry Mij of M, subtract Kronecker delta, apply it to such object, you get also 0. Now, with these two equations, we could solve this equation. This is an integral equation, and we obtain these equations. So we get this T minus and T plus in terms of M21 and M11, and I have an explicit formula for M11 and M21. Just integrate H, you get that. And then we did actually calculate to see how the scattering amplitude will look like using our basic formula. And amazingly, we discovered that the end result had this form, which is precisely what you would get from firstborn approximation. It was total surprise. It just happened that this, I recognize this as what the firstborn approximation would give you. So that completes the proof. The firstborn approximation is exact under this condition. Again, there is no approximation involved. This is exact result. Now, since out of the expression of the firstborn approximation, you can determine the potential by taking inverse Fourier transform, you can use this result for some sort of inverse scattering, which I call constrained inverse scattering. What I mean by that is that this condition double star is not very, very restrictive. Again, you can play with it. There are infinitely many potentials which satisfy this condition. Now, the aim is, well, put more conditions so that the scattering amplitude satisfies certain nice properties that you desire. Since you know the explicit formula for the scattering amplitude, that's very easy now. So we used it for realizing what is called unidirectional invisibility in 2 dimensions. What do I mean by unidirectional in 2 dimensions? What I mean is the following. Well, you can do scattering in 2 dimensions by placing your source at -infinity along x or +infinity. And when the source is at x, the plane x equal to -infinity, I call the wave left incident wave. And if the source is at the plane x equals to +infinity, I call it right incident wave. And if your potential is invisible when the source is placed at -infinity, you get left invisibility. And if the source is at +infinity and the potential doesn't scatter it, then I call the potential right invisible. So the question is, can you find a potential which is left invisible only or right invisible only? That it scatters from one side, but it doesn't scatter from the other side. And I want this to happen not at one or discrete values of the frequency or wave number, but in an extended interval of frequencies or wave numbers. So this is the outcome. Using this exactness of the firstborn approximation, we could get this set of further conditions. The first one just makes the Born approximation exact, and the other 2 essentially makes it right invisible for you within this interval. Again, alpha is free parameter, so you can make this interval as big as you wish. And you can get examples. This is one example, and you can make it an example in electrodynamics. This is again 2-dimensional permittivity profile with some free parameters that makes it unidirectionally right invisible for every transverse electric wave with wave number between alpha over √2 and alpha. Okay, this brings me to the last topic. I guess I have still 7 minutes, that's good. That is delta function in 2 dimensions. This has very old history. Since 1960s and 70s, people knew that 2-dimensional delta functions have problems. It leads to divergences. And to deal with them, you can do regularization and renormalization. And this is a very nice example to teach the idea of renormalization for students. So let's look at this 2-dimensional delta function. Z is the coupling constant, which I can allow to be complex. The potential can be written like this. Just take its, put x bra and psi ket, and you'll see that you get action of the delta function. Now remember the formula for the definition actually of the scattering amplitude. You substitute it here, you get that. And also we have this formula, which was the Lippmann-Schwinger equation in the position representation. Once you substitute this here and here, you get this formula for F and this formula for psi of R. So in order to get F of theta, I just need to put 0 here and put the substitute the result there. Well, if you put 0 and do the manipulations, you get this formula for 0 psi, and you substitute in the formula for F theta, you get this. And remember, the propagator is Hankel function in 2 dimensions. And the end result of your calculation will be this. So it seems that everything is simple, but the problem is that the Hankel function at 0 blows up. So it seems that this calculation tells you that F of theta is identically 0 for all frequencies. That means point scatterers don't scatter, which is not true. It violates, for example, the uniqueness of inverse scattering. You can't have a potential which doesn't scatter for all frequencies, because that is the property of the vacuum. So what you do, you try to regularize this infinity. There are various ways of regularization. One of the simplest is to make 0 into something which is small. And this small parameter rho is actually the linear size of your point scatterers. Really, a point scatterer does not exist. It means a scatterer which is much smaller than the wavelength. So it will have some dimension, a linear dimension I call rho, and I will take this rho to be very, very small, much smaller than the wavelength. So k times rho is much less than, much smaller than 1. And then after regularization, you do a coupling constant renormalization. You allow your coupling constant to depend on this rho. This is the scale of renormalization now, in such a way that what happens in the denominator, which is physical quantity, should be finite and should be independent of the renormalization scale. So you obtain this formula, which is the same as before. I just have that rather than zeta, I have zeta of rho, and rather than 0, I have k times rho. And since k rho is very, very small, I look at the asymptotics or the expansion of the Hankel function for a small argument. This is the series expansion, and you see this is the origin of this singularity. You have a logarithmic singularity. And you do renormalization by demanding that the zeta has become renormalized coupling constant, which is defined by that. So you essentially put this infinity inside here and then subtract it out. So with this procedure, you substitute this here, you get this formula for the scattering amplitude. So the formula is very simple. It's minus √2 over pi, the renormalized coupling constant, over 4 plus I times renormalized coupling constant. Okay, now let's do it our way using this transfer matrix formalism. Again, to remind you, I need to calculate the transfer matrix M. From the transfer matrix, I should get this T minus T plus and put it here, get F. So we first calculate the transfer matrix, and then we solve this equation, which is the same as this equation. It's an integral equation. The transfer matrix, again, this is the Dyson series expansion. This is the form of the Hamiltonian. And now I have the potential to be this. I substitute this formula for the expression for the Hamiltonian, and this is what I get. I haven't done anything. Just rather than V, I wrote Vx, and this Y has become I del P. A nice thing about this Hamiltonian is that its square, that is quadratic term, will involve 2 copies of k, and k squared is 0. So the series truncates. This is the transfer matrix. Now, what about this operator? So remember, I'm missing an I here. This operator will act on a test function according to this convolution formula, in which the Fourier transform of potential with respect to y appears. This is delta of y, so its Fourier transform is 1. So this is just 1. So this operator just integrates the test function, doesn't do anything else. Well, from here, I should solve this integral equation, substitute the result, get t plus, and once you do that, you find out that t plus and t minus are equal and given by this formula. You take t plus minus, substitute in the formula for the transfer, the scattering amplitude, and you get precisely the same formula renormalization program gives you. The only difference is that there is no regularization, there is no renormalization. This is the coupling constant which appears in the expression for the potential. Somehow, this method that we have developed avoids all the problems with infinities of point scatterers. Well, we have used this method for various other solving various other problems. For example, we could get exact solutions for the scattering problem for arrays of 2-dimensional delta functions which lie on a straight line, arbitrary arrays with arbitrary coupling constant and arbitrary position of the delta functions. We could solve potentials of this form. There's a delta function along x-axis, and then the y dependence is an arbitrary periodic function. And one example of this is the Dirac-Combs in 2 dimensions. That's a periodic array of 2-dimensional delta functions lying along a straight line. And for all of these potentials, we really mean we solve it exactly. We have explicit expression for the scattering amplitude in terms of the classical and some special functions, essentially Bessel functions, and nothing more than that. Another example, which is very interesting, is the following. Suppose you have a potential which vanishes when x is outside 0 and a. This is a kind of a slab, a grating. And inside this interval, it has this form. This V0 of x is some potential for which you know the solution in 1 dimension. And V1 of x is an arbitrary complex potential, scattering potential. The y dependence has this periodic form. And for this also, we could solve the scattering problem in a complete exact form. And the solution is very interesting. If the wave number of the wave that you send is less than this alpha, alpha comes here inside the potential, then this potential does not change the direction of the incoming wave. Parts of it transmits like this, and parts of it reflected as if it's just 1-dimensional problem. But once you increase value of k beyond alpha, and when k is between alpha and 2 alpha, there will be 2 rays coming with particular angles. And then once you increase it, there are 2 more and 2 more. So there's like creation of a scattered wave in pairs. And we have explicit form of the amplitude and the direction of these waves. These scattered waves are a kind of entangled because they have opposite momenta. And it's very interesting to see that the y component of these momenta are quantized. So we thought it can be helpful for people who do quantum computations. And this is the explicit form of the scattering amplitude for these. You can arrange your parameters so that these amplitudes actually blow up for certain frequencies. And that is a sign of spectral singularity. So you can use this in optics to produce some lasing effect. And because it happens for particular angles, these are lasers which shine along particular angles. So it gives you a way of directional lasing. It also provides an additional laser mode, which can be useful, but I don't have time to discuss. Okay, so let me conclude. All I said today lies on this kind of magic formula. The transfer matrix is the time-ordered exponential of some effective Hamiltonian. We could use it to develop the notion of transfer matrix in 2 dimensions. There are various applications of this formula in 1 dimension that I did not discuss. And this gives, in 2 dimensions, a new formulation of scattering theory. We could use this formulation to achieve broadband invisibility, the idea of potentials with identical scattering properties below some critical energy. The first example ever of potentials for which the Born approximation gives exact result were obtained using this method. I showed you how you can achieve broadband unidirectional invisibility. This was also not even thought of before. And I also discussed how this method avoids the problems of renormalization when dealing with point scatterers. And finally, I just mentioned that this method can be used to obtain previously unknown exactly solvable potentials. What I did not talk about was natural questions. Do these results generalize to 3 dimension? And the answer is yes. And every paper we wrote, I think almost all of the papers we wrote on these topics have a section called generalization to 3 dimensions. Everything generalizes to 3 dimensions. The algebra becomes a little more complicated, but essentially there's no conceptual difficulty. Another important development is, can you do this for scattering of electromagnetic waves? Well, this is much harder than scattering of scalar waves because this is vector waves. And we were able to generalize it for scattering of electromagnetic waves by isotropic media. And in one particular application of it was to try to get permittivity and permeability profiles which make the medium broadband invisible for all electromagnetic waves, not just for TE waves. And this is possible. This is just published last month. This is the list of basic references. This red one is about electromagnetic waves. This is the first one, which has information about point scatterers. Okay, with that, I thank you very much. I think I'm over 3 minutes over.
You're still muted. Unmute everybody again. Yeah, and please. So if you want to ask a question, you can unmute yourself now.
I have a couple of comments.
Sure.
Hello, is it my turn? Okay,
Yeah,
yes.
we can hear you. If
Yes,
everyone is quiet and lets Philip speak, then go ahead.
Okay, I have a couple of comments, Ali, about the going to 3 dimensions. What happens for the Coulomb potential is that the Born approximation for the scattering amplitude is absolutely wrong, but the Born approximation for the cross section is absolutely right. And the reason is the exact solution to the Coulomb scattering is the Born amplitude time, the first first approximation to the Born amplitude times a phase. And the phase drops out when you take the modulus squared. So there is at least one example where the first Born approximation actually agrees with observation. And this is very important because Rutherford didn't know any of this. And yet when he calculated the scattering of a 1 over r potential, he got the right answer. And the reason he got the right answer was because the phase doesn't appear in the cross-section. So maybe there's maybe if you can't generalize your two-dimensional result to 3 dimensions for the amplitude, you may still be able to generalize it for the cross-section. That was my comment.
Okay. The Coulomb potential is long-range potential. So
Yes.
at this stage, I mean, our method only works for short-range potentials, but asymptotically they are plane waves. But there are, we have done some work to extend it to long-range potentials.
Mm-hmm.
Thank you.
Good.
Can I ask a question?
Sure, Olaf.
Yeah, in your quasi-exactly solvable cases, when you approach with the wave number, when you approach alpha, then somehow the first approximation of the firstborn term will cease to be correct, and the higher order terms will kick in.
That's right.
Is that somehow analytic, or will there be some kind of singularity, some non-analytic behavior? Will all higher born waves come in immediately, simultaneously, or what happens there?
Well, you see, we haven't explored that analytically because we don't know whether it is exact. But in principle, you can calculate those orders. We actually checked, and that precisely happens. Once you cross that frequency, the second order corrections become non-zero.
Yes, but the higher ones remain zero?
Well, but we haven't checked the third order. Yeah.
Thanks.
You're welcome.
Okay, may
Any
I
more
ask a
questions?
question? Yes, I have a very simple one.
Mm-hmm.
You use the word omnidirectional. I have a concern about that word. Since your X and Y obviously are arbitrarily chosen, but from your procedure, it seems X should be where the incoming wave is, which is a plane wave in that direction. And then you detect it in, say, incoming in minus infinity and outgoing at plus infinity. If you didn't see anything there, or didn't see any disturbance there, is invisible. But this is only invisible in that particular direction. It's not
No. Let me try to find the correct. Yeah. So this is the scattering setup. The incident wave comes with an arbitrary angle.
Okay.
So when I say omnidirectionally invisible, it means that for all angles, it is invisible. So I'm not sending the wave along the x-axis. Theta 0 can be anything from minus pi over 2 to pi over 2.
I see. The observation is in large X, but on another side, but it's also in any direction?
Yes, I mean, this is the incident. Can you see the?
Yes, I can, yeah.
So this is the incident wave number.
Uh-huh.
And its angle is arbitrary.
But my question is, since your eventual formula obviously taking X and Y direction in not symmetric way, you Fourier transform Y instead, and you keep X. But this choice should be arbitrary, right?
Yeah, it's absolutely arbitrary.
But your result is well, actually my question would be, is your result depend on this choice, which direction you call it X or which direction you call it Y?
No, it doesn't. You see, since I have picked this theta 0 arbitrary, And theta 0 doesn't enter into the invisibility result. I mean,
Okay.
it is out there.
Can I ask a question?
Sure.
Hello. Yeah. So when you consider the regularization and renormalization, is that a exact or in some perturbation theory? Because you are comparing the result with the exact result coming from Born approximation.
No, first of all, for delta function, I didn't use Born approximation. I just solved it, right? This is, I'm not saying that, I mean, I just used the definition of the delta function potential to get the, let's see. So I just used the expression for the potential to find the transfer matrix and these amplitudes T minus T plus and F. So this is completely independent of the previous topic on Born approximation.
No, this my question is that the regularization and renormalization you use, is that only for this is exact or it is some perturbation theory like first order?
No, it is exact. You see, if you look at the expression, you see it's not a polynomial in zeta tilde, right? So all hours of zeta contribute. So it is not perturbation theory or anything.
Yeah, for some complicated potential, can we compare the result in order by order in renormalization as well as from the Born approximation?
Yes.
Is that possibility?
Well, you can try to solve the two-dimensional delta function by performing Born approximation. What happens is that the first Born approximation gives you a finite result, but starting from the second Born approximation, you encounter infinities.
Okay. Okay, thank you.
Okay.
Can I ask a question?
Sure.
Yes. Very nice. First of all, very, very nice talk and very, very interesting research. I would like to ask you actually two questions with your permission. One is about if you have a defect, because I know you have worked on defects, and if you have a defect in your two-dimensional, let's say, suppose you are in a solid state chain, spin chain, and there is a hole. Are the results valid if in the presence of defects for the scattering of defects or not? That's my question.
So we try to model defects by these delta functions.
Right.
So in two-dimensional delta function becomes a line defect in 3 dimensions. And one of the applications of this result was to get the lasing from a slab which has a line defect.
So they would be valid in this.
Yes.
The second one is, what about curved space-time? Suppose that you have a curved space-time in 2 dimensions. You think you can
Well, if you actually, there's a project we are working on it.
Oh, right. Sorry.
So if you can formulate your problem and turn it into a scattering problem in 2 dimensions, yes, you can.
Then yes.
Yeah.
So it depends on the kind of defects that you have, for instance, or
Yes.
on the curved space-time. Thank you. Thank you very much.
Any more questions? I have a very general one, Ali.
Sure.
H square is 0. That reminds a little bit on supersymmetric variables. Can you draw some analogy to this, or is this too vague?
In this case, you see this H is an integral operator. Somehow its square, its kernel and its image coincide. That you multiply, you get 0. So I don't know if you can make any connection with what happens in supersymmetry. I don't know.
Can I make a comment on Nikos' comment? Am I live? Yes.
Yeah, go ahead, Phil.
Yes. Yeah, what happens if you put a defect in a crystal is you break translational invariance, which means that the eigenstates are no longer plane waves, but you can still construct a complete basis. It's just basically distorted waves. And I think Ali's approach isn't restricted to plane waves. It's restricted to a convenient, complete basis. So it may well generalize.
Yes, so when I replied, I thought about doing scattering by a substance, material with defect. And then that defect you can identify with some delta function. But this is when this object is in vacuum, so you send wave in vacuum. But what you're saying is what happens if you do wave propagation inside some solid state material. Well, we don't know, as you say. I mean, it's a wide open area.
Well, I think you'll have to solve that one before you can go to curve space.
Well, it depends. It may be a defect-free curve space.
Maybe I can make a remark to Andreas' question of supersymmetry. It seemed to me that it was crucial for the vanishing of the second order that this matrix K, this 2x2 matrix, squared to 0. So in some sense, one could just look for matrices who are nilpotent to a certain order, and that would correspond to a potential that just whose Born approximation just becomes exact after that order. Because the space of matrices is not a number field, so we can always find zero divisors there. You know, not sure whether that's related to supersymmetry. Seems to be an algebraic property of suitable matrices.
But I should make some clarification. This K squared equal to 0 only applies for two-dimensional delta function.
Okay.
For the other cases with Born approximation, this H squared vanishes not because you get K squared. It has to do with this integral operator, which involves this form of the potential.
Okay.
So it's not algebraic. It's just
I see. Okay, thanks.
analytic.
I also make a suggestion for the future. You introduced this operator V of X and ID by dP, and you showed that if it's 0, then you get invisibility. But can you go the other way? Can you show that if you have invisibility that V has to have that form, or could there be some even more general form for V that would do the job?
So I don't think so. It's like in quantum mechanics, you can arrange to have cyclic states after particular values of time, but that does not mean that your Hamiltonian is 0, right?
Well, I mean, so maybe your result isn't. You showed that it's sufficient. Maybe you can show that it's necessary as well. That was all I meant.
Well, I think it's not necessary.
Ah, well, that's fine. That's what I was asking.
Okay.
I have a question.
Sure.
I thought so this is coming back to the story of whether you have an exact result in the Born approximation. So I thought the point of pseudopotential, so sometimes called the Fermi-Huang pseudopotential, these are something that gives the exact scattering amplitude when you calculate them using the first Born approximation. So I'm wondering how that connects to your statement of exactness. So maybe the usual statement of the Fermi-Huang one is only a low energy approximation.
Probably. Well, I haven't thought about it, but in this pseudo potentials, presumably you cannot compute them in an exact way, right?
Well, you're only trying to reproduce the asymptotic scattering properties of a potential, but by replacing it by a delta function, basically. And the idea is that within the first Born approximation, you exactly reproduce the exact scattering problems, but maybe it's limited to just the scattering length or something. I mean, normally you put in a very limited amount of information, so the scattering length or something like that.
Yeah, I don't think you can get I mean, the statement I wanted to make is this: I have a potential for which the firstborn approximation is exact, with no approximations. So I'm not taking anything small or large.
Yeah. Okay.
In other words, the higher order corrections all vanish.
Mm-hmm. Yeah, maybe it's a different philosophy from the normal pseudo potential.
I think so.
Approach. Because in the Huang sort of Fermi pseudo potential, the idea is you replace the true scattering potential by some boundary conditions applied through a delta function.
I see.
Yeah, I mean, it's a clever way of dealing with many particle scattering, because you no longer have to deal with actual potentials. You replace everything by boundary conditions on a surface,
Mm-hmm.
on some hard sphere usually.
Yeah.
There are any further questions, comments?
Well, have we reached the end of our general discussion? Because I'd just like to say a few words for everyone to thank Andreas and Francisco for putting this together. I think it's an exceptionally good idea, and I think we're all getting a lot out of it. And Ali has set us off in the right direction, and I think this is a very good, and well done, both of you, and well done, Ali, as well.
Yes.
Thank you.
Yeah. Thank you very much. And well, also, of course, thanks to Ali for the nice talk, and also all of you for the participation. So maybe if there are no any further comments, so we must say goodbye, and we see each other until next week with the talk of Nick, right? Same time.
The time is different, I think, next week, or is not at 3 o'clock, or it is always the 3 o'clock? I don't remember.
We fixed at the same time as well so far.
It's the same time. No,
Same
I'm
time.
just asking.
Yes, the same time.
Thank you very much.
Okay.
Looking
Thank
forward.
you.
Yes.
Bye-bye.
Okay. Thank you very much.
Thanks for
Thank you very much, Ali.
Bye.
Thank you all of you. Bye bye.
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 Hey.